In today's lesson, I'm going to go through some calculations with you for both strong and weak acids and bases. So we're going to calculate H3O plus and pH both in strong and weak acid solutions. For strong acid solutions, the calculations are actually very simple. So as an example here, what is the H3O plus and the pH of a 0.10 molar HCl solution? So we know HCl is a strong acid. I've listed the 6 strong acids that you need to know here at the top, and they're in your notes too as well. And so since HCl is a strong acid, it's going to dissociate completely. So every HCl molecule is going to give us one H3O plus anion or cation. And so if we have 0.1 molar HCl, we're going to get 0.1 molar H3O plus. All right, and I went over in the last video that the pH is equal to the negative log of the H3O plus concentration. So that's going to be equal to the negative log of 0.10, which is equal to 1. Okay, for weak acids, the situation is a little bit more complicated because for a generic acid, HA, so this could be any weak acid, we know that it reacts with water, and some of it will dissociate and make H3O plus and A minus, the conjugate base for HA. And how much that happens is expressed by Ka. So Ka is our concentration of H3O plus times the concentration of A minus divided by the concentration of HA. Okay, so the bigger Ka is, the more that acid will dissociate, and the smaller it is, the less it will dissociate. So here we have an example. What is the H3O plus concentration of a 0.1000 molar HCN solution? And the Ka of HCN is equal to 4.9 times 10 to the minus 10th. Okay, so to do this, we're going to need to use an ice table. And so we'll have HA, H3O plus, and A minus as the 3 things that we can have concentration of. So we're going to ignore the water because it's a liquid. All right, so our initial concentration of HA is 0.100. All right, we are essentially starting out with 0 H3O plus and 0 A minus. Okay, so the change in our equilibrium is going to be minus X for the HA and plus X for the other 2. Right, so at equilibrium we have 0.1000 minus X, and for H3O plus we have X times X, all right, X for H3O plus and X for A minus. So if we plug all of those into our Ka equation and set it equal to 4.9 times 10 to the minus 10th, then we can solve for the concentration of H3O plus. So we have 4.9 times 10 to the minus 10th equals X squared over 0.1000 minus X. And remember from our equilibrium chapter, if the exponent in our Ka if the absolute value of that is bigger than 5, then we can ignore that minus X because it's very small. Okay, so that simplifies our equation to just X squared over 0.1, right? And if we solve for X, we get 7 times 10 to the minus 6th. Okay, and you can see that if we did 7 times 10 to the minus 6, if we subtract that from our 0.1000, the number isn't going to change. All right, so then that means our hydronium ion concentration is 7 times 10 to the minus 6, and if we do the negative log of 7 times 10 to the minus 6, we get 5.155 as our pH. Okay, so here's another example just to give you some practice. What is the pH of a 0.2 molar HNO2 solution if the Ka is 4.6 times 10 to the minus 4th? Okay, so we need to set up another ice table. So here we're interested in the concentration of HNO2, the concentration of H3O plus, and the concentration of NO2 minus. Okay, so the initial concentration of HNO2 is 0.200. And the others we'll assume are about 0. The change is going to be minus X, and then plus X and plus X, which gives our equilibrium concentrations as 0.2 minus X and X and X. Okay, in this case, you would get an answer that's pretty darn close to the right answer if you ignored the X here that we're subtracting, but this exponent is -4, which is not quite a large enough number for us to ignore it. So you can either, if you know how to do this on your calculator, you can do it that way, or it's pretty easy to find quadratic solvers online as well. So when we set this up, we get 4.6 times 10 to the minus fourth equals x squared over 0.2 minus x. Okay, and if we solve the quadratic for that, we get 9.36 times 10 to the minus 3. Okay, and that's our H3O plus concentration. So we have the pH equals negative log of 9.36 times 10 to the minus 3, which equals 2.03. And that's our pH. All right, this problem is set up a little bit differently. Here we're actually trying to find the Ka and we're given the pH. So again, it's not 100% required that you use the ICE table here, but I think it helps organize your thoughts. So in this case, we have HA and 0.1 is our initial concentration, and minus X will be the change. And we start with 0 of A minus and of H3O plus, and the change for those will be plus X and plus X. Okay? So our equilibrium concentrations are going to be 0.1 minus X, X, and X. Okay, so if we put that into what would be our Ka equation, then we have Ka is equal to x squared over 1 minus x. Okay, and in this case, since x is our H3O plus, we're going to have to use the pH to find H3O plus. So we know that pH is equal to negative log of the H3O plus concentration, and we know that our pH is 4.25. So this, if you haven't covered logs in another class, you're probably just going to have to remember that this is how you solve this, but the log is base 10, so you just do 10 to the minus 4.25, and that will give you the H3O plus concentration. Okay, so the concentration is 5.62 times 10 to the minus fifth molar. Okay, and then if we plug that in for our X, both for A minus and for H3O plus, and you could plug it in for HA, but you can see this number is so small that when we subtract it from 0.100, it's not going to make a difference. Okay, so our Ka is equal to 5.62 times 10 to the minus fifth squared divided by 0.1. which is equal to 3.16 times 10 to the minus eighth. All right, the last thing we're going to cover in this part on acids is percent ionization. So the percent ionization is equal to the concentration of ionized acid divided by the initial concentration of the acid times 100%. So it's going to be basically the concentration of H3O plus at equilibrium divided by the HA that you put in initially times 100. Okay, so let's do one of these problems as practice. So if we have a 2.5 molar solution of HNO2, then the first thing we need to do is figure out how much of that HNO2 ionizes. So we're again going to need an ICE table to do this. The initial concentration of HNO2 is 2.5, and the others we'll just assume is 0. We're going to do minus X for the change for HNO2 and plus X for H3O plus and for NO2 minus. So our equilibrium concentrations are going to be 2.5 minus X and X. So the Ka for this, we already know, is 4.6 times 10 to the minus fourth, and that's going to equal X squared over 2.5 minus X. Okay, so if we solve for X, we get 0.034. And that means that the concentration of H3O plus is 0.34. So we can do that divided by our initial concentration, which was 2.5 molar, and times 100%, and we'll get 1.4% ionization. So really not very much of this acid ionizes at all, and that is consistent with the Ka value being fairly small. Now let's spend a little bit of time talking about bases. So a strong base, just like a strong acid, is one that dissociates completely in solution. And a weak base is one that dissociates some, but does not dissociate completely. Okay, just like a conjugate base was what was left after the acid reacted, a conjugate acid is what's left after a base reacts. So after a base accepts a proton, you have a conjugate acid. Okay, so as the base gets better at taking a proton, it gets worse at giving up that proton, and vice versa. So as base strength decreases, conjugate acid strength increases. Okay, so let's practice writing some equations with bases and water, since we did some with acids. So if we have NH3 that reacts with water, all right, the base is going to accept a proton, so it's going to become NH4 plus, and we'll be left with OH minus. Okay, the second one we have is carbonate ion. So CO3 2 minus, if that reacts with water and accepts a proton, it will now be HCO3 minus plus OH minus, or it could react with two waters if we want to fulfill both of those and become H2CO3. Okay, either of those is possible. And then the third one we have here is we have CH3COO minus. Okay, so you should recognize that COO as part of the organic acid group that I told you about before, but this one is missing its proton, so it's going to react with water to take that proton back. And so it's going to, the products will be CH3COOH and OH minus. Now, just like we had an equilibrium constant with acids, we also have one with bases. So this is called the Kb in the case of a base, for B for base. And so the base ionization constant, or Kb, is equal to the concentration of BH plus, so that's the base after it takes the proton, times the concentration of OH minus, divided by the concentration of the base at equilibrium, or B. Okay, so for strong bases, just like this was really straightforward for strong acids, we can do these calculations very easily. So what's the OH minus pH, the pOH and the pH of a 0.10 molar NaOH solution? So if we have a solution that is 0.1 molar NaOH, then all of that dissociates, and so we have 0.1 molar OH minus when we finish. Okay, and so the OH minus concentration is just going to be that 0.1 molar. The pOH, just like the pH, is the negative log, but in this case it's the negative log of the OH minus. So the negative log of 0.10 molar is going to be 1. Okay, so the pOH is 1. And then the pH, when we're in water, we're on a scale, from 0 to 14, essentially. And so the pH is going to be 14 minus the pOH. So those two numbers are always going to add up to 14. So if the pOH is 1, then the pH is going to have to be 13. So this is a very basic solution. So now let's do the same thing for a weak base. So if we have any generic base B and we add it to H2O, we're going to get BH plus OH minus. Okay, so what is the OH minus concentration of a 0.100 molar NH3 solution, where the Kb is equal to 1.76 times 10 to the minus fifth? So just like with the acids, we're going to need to write an ice table out. So the chemicals that we're interested in this case are the NH3 concentration, the NH4 plus concentration, because that's our BH plus, and the OH minus concentration. So our initial concentration of OH minus is going to be 0, and for the NH4 plus will also be 0. The initial concentration of NH3 is going to be 0.100 molar. Okay, so we're going to have minus x, and plus x for our change, and then at equilibrium, we'll have 0.1 minus x, and x. All right, so we're going to plug that into our Kb equation and set it equal to 1.76, so we get, times 10 to the minus fifth, so we get 1.76 times 10 to the minus fifth is equal to x squared over 0.1, and we can ignore the minus x because our equilibrium constant is sufficiently small that we can ignore it. Okay, so when we solve for x in this case, we end up with x equals 1.33 times 10 to the minus third molar. Okay, so now we need to figure out what the pH of the solution is, because that's our next question. What is the pH of the solution described above? And we can get this by using our Kw, which I mentioned in the last video. So Kw is equal to the concentration of H3O plus times the concentration of OH minus, because those are the things that ionize when water goes through the autoionization, and that is always equal to 1.00 times 10 to the minus 14th. So this is where our pH equal 14 comes from. Okay, so if we plug in our OH minus concentration here and solve for H3O plus, we get H3O plus is equal to 7.52 times 10 to the minus 12th molar. And if we take the negative log of that, we get the pH equals minus log of 7.52 times 10 to the minus 12th, and that comes out to 11.124 for our pH.